What if a world everyone dismissed as frozen and dead has been quietly running one of the strangest climates we have ever found anywhere in the solar system? For nearly 2 decades, Pluto has been treated like an afterthought, a tiny frozen rock at the edge of the solar system, voted out of the Planet Club in 2006, written off as nothing more than a distant icy chunk that nobody really needed to think about again. But the James Webb Space Telescope has just looked at it again, and the picture it sent back is almost impossible to believe. Before we go any further, if you love stories like this, the kind that make you rethink what you thought you knew about the universe, hit that subscribe button, tap the like, and share this with a friend who would lose their mind over it. It really helps the channel, and you will not want to miss what we have coming next. Here is what Webb has uncovered in the last year alone, and why a dwarf planet on the very fringe of the solar system is now sitting at the center of one of the most exciting scientific debates of our entire generation. In 1930, a 24-year-old assistant named Clyde Tombaugh was working at Lowell Observatory in Flagstaff, Arizona. His job was almost insultingly simple. He sat at a machine called a blink comparator, comparing photographs of the same patch of sky taken on different nights. He was looking for a single dot of light that had shifted position between exposures, week after week, photograph after photograph. He was 24 years old, working with technology that looks laughably primitive by today's standards, and he was searching a sky that no human being had ever searched at that depth before. He found it. A tiny dot that had moved. That dot turned out to be Pluto. The find made global headlines. For most of the next 85 years, no spacecraft ever visited this frozen little world. Year after year, decade after decade, it sat there in textbooks and in the public imagination as the 9th planet, with very little new to say about it. Everyone assumed it was a dead, frozen, mostly boring chunk of rock and ice drifting at the edge of everything. That is, until July 2015, NASA New Horizons. Spacecraft finally arrived at Pluto after a 9.5-year journey across nearly 3 billion miles of empty space. It had been launched in 2006 on a mission that almost did not survive cancellation, and it had one single shot, one flyby, one narrow window of a few hours. No orbit, no second pass, no margin for error. It flew past Pluto at more than 30,000 miles per hour, snapped everything it could, and then disappeared deeper into the Kuiper Belt, never coming back. What it sent back rewrote the textbooks in real time. There was a vast, pale, heart-shaped plain of nitrogen ice, roughly the size of Texas, that looked so smooth and so young that geologists openly admitted they did not know how to explain it. There were mountains made of frozen water ice taller than anything in the Rockies, so incredibly cold that water ice behaved more like granite than anything you would picture when you hear the word ice. There were layers of blue haze rising hundreds of miles above the surface, lit by the distant sun, layered and structured in ways that told scientists something active was happening in that thin nitrogen atmosphere. And there were enormous reddish-brown stains covering the north pole of Pluto's largest moon, Charon, that nobody could fully explain and nobody could stop staring at. New Horizons answered decades of questions and opened roughly twice as many new ones. Almost everything it could not resolve with a single flyby became a question that the next generation of telescopes would have to take up. The big question was, who would pick up that next chapter and how long would it take? That is exactly where the James Webb Space Telescope comes in. Webb is not really a camera in the traditional sense. Not only that, its most powerful tool is something called spectroscopy, which is the art of splitting light into its individual wavelengths with extraordinary precision. This allows you to read the chemical fingerprints of whatever you are looking at. Point that instrument at a faint dot of reflected sunlight 4 billion miles away, and it can tell you what molecules are sitting on the surface. It can tell you what the atmosphere is made of, how warm each layer actually is, and how all of those things are changing over time. All of this is done without physically going anywhere. For a place like Pluto, this is the magic that nobody had before. But there was a catch that slowed everything down for years. From the point of view of Earth, Pluto and Charon sit so close to each other in the sky. Any older telescope, when it tried to read the heat coming from Pluto, accidentally picked up heat from Charon sitting right next to it in the same field of view. The two signals blurred together into mush. That blurring problem blocked serious thermal analysis of Pluto for nearly a decade. A Webb, much larger mirror, and its extraordinarily sensitive mid-infrared instrument, called MIRI, finally solved that problem. For the first time in the entire history of Pluto science, researchers could read Pluto-owned thermal emission cleanly, separated from its companion moon. That single technical breakthrough is what unlocked everything that came next. A team, led by astronomer Tanguy Bertrand at the Paris Observatory, used Webb data collected back in 2022 and 2023. What they found, and published in Nature Astronomy in June 2025, confirmed a prediction that planetary scientist Xi Zhang had made back in 2017. Zhang had proposed something that even some of his colleagues openly called a crazy idea. He suggested that the haze particles floating in Pluto's extremely thin atmosphere were not trapping heat the way similar haze traps heat on Saturn moon Titan. Instead, he argued that the haze was doing almost the exact opposite. It was absorbing sunlight during the day. It was then radiating that energy straight back out into space as infrared heat, faster than Pluto's thin atmosphere could hold on to it. In other words, the haze was not acting like a blanket at all. It was acting like a radiator. It was actively pulling heat away from a world that barely had any heat to spare in the first place. Bertrand and his team found that Webb data confirmed this directly. The haze particles in Pluto's upper atmosphere are genuinely controlling its entire energy balance. They do this by heating up and cooling down as they absorb and emit radiation. The net result is that Pluto's upper atmosphere runs roughly 30 degrees Fahrenheit, colder than every existing climate model had predicted it should be. Bertrand himself told reporters, "This represents a genuinely new kind of climate, unlike any other atmosphere in the solar system we have ever studied. On every other world we have looked at carefully, the gases themselves do most of the climate work. On Pluto, the tiny solid particles suspended in those gases appear to be the ones running the entire show." And the researchers made one more striking observation. If haze-driven cooling can happen on Pluto, it might also be happening on other distant hazy worlds. This includes Neptune moon Triton, and it may even have played a role in the cooling of Earth's own ancient atmosphere billions of years ago. That connection to early Earth is worth sitting with for a moment. Pluto's atmosphere is mostly nitrogen, with methane, carbon monoxide, and traces of other compounds. That composition is broadly similar to what many researchers believe Earth's atmosphere looked like in its very earliest era. This was before photosynthesis transformed everything and turned it into the oxygen-rich world we live in today. Sunlight hitting those early Earth molecules would have driven the same kind of photochemical reactions that sunlight drives on Pluto right now. Reactions that produce organic compounds, reactions that build up haze, reactions that slowly distribute chemistry through the atmosphere and onto the surface below. Pluto, frozen in deep freeze for billions of years, has been quietly running a version of that ancient pre-life atmospheric chemistry for roughly 4 billion years. It is not just a curiosity anymore. It is a working model, in real time, of conditions that preceded life on Earth. These conditions no longer exist here in any accessible form anywhere on our planet, and that photochemistry produces something visually striking on the surface. The dark reddish-brown material that colors large parts of Pluto's surface comes from compounds called tholins. This is especially true in a broad equatorial band roughly the size of Alaska. Tholins form when ultraviolet sunlight breaks apart methane and nitrogen molecules high in the atmosphere. The fragments recombine into heavier and darker organic compounds that are too heavy to stay aloft and slowly drift down to accumulate on the surface. They belong to the same broad chemical family as some of the molecules that researchers believe may have played a role in the chemistry that eventually led to life on early Earth. Here on Pluto, that same slow production of biological building blocks has been running for billions of years. They are settling quietly onto a surface too cold for any of it to do anything interesting. A 4 billion year snowfall of organic chemistry, landing on a world where temperatures sit between roughly minus 369 and minus 387 degrees Fahrenheit. At those temperatures, the nitrogen you and I are breathing right now would freeze solid and become part of the landscape. Those temperature numbers deserve a moment. Sunlight reaching Pluto is roughly 1,000 times weaker than sunlight reaching Earth. Surface temperatures sit between roughly minus 387 and minus 369 degrees Fahrenheit. The atmospheric pressure at the surface is so low it is hard to write down without sounding exaggerated, only about 13 microbars. This is compared to 1 million microbars here on Earth. Even standing on Pluto in a perfectly designed suit, the cold would reach exposed surfaces almost instantly. This would happen long before the absence of breathable air became the immediate danger. Now, if you have made it this far, you are clearly someone who loves going deeper into stories like this. If this kind of science is what you are here for, drop a quick comment below. Tell me, what would you want James Webb to look at next? And I will read every single reply. Your ideas genuinely shape what we cover next on this channel. Now, here is the part of the story that made the rest of the scientific community stop mid-sentence. In June 2026, a separate research team, again based out of the Paris Observatory, submitted a paper reporting a detection that they described in unusually direct language. While analyzing Webb infrared data from both Titan and Pluto, in a narrow wavelength window around 511 micrometers, they found an absorption feature. This spectral zone was chosen because haze absorption is low enough that the telescope can see through the atmosphere down to the surface. The researchers found a specific dip in the light spectrum where something was clearly absorbing the light, and they could not identify what it was. They searched the entire published planetary spectral literature, but found nothing. They found no documented molecule, no known gas, no confirmed ice compound on any solar system body that produced this result. Not even on any exoplanet ever spectroscopically surveyed, Is there an absorption signal at that exact wavelength? They proposed several theoretical candidates, including certain hydrocarbon configurations or a benzene molecule mixed with an unknown partner. Other candidates included acetylene or even quinone ice. None of those candidates has been confirmed. The authors were explicit, even a little blunt. They cannot yet say what the molecule is. But here is what makes this finding so extraordinary. The feature appeared twice in the Titan data. It came from two separate Webb instruments operating in two different wavelength ranges, with observations collected months apart. And then it appeared again in Pluto, data from May 2023, at essentially the same wavelength. Two utterly different worlds sharing an absorption signal at a wavelength that matches nothing in our entire scientific database. Titan is roughly 4 times closer to the Sun than Pluto, significantly larger, and has liquid methane lakes and rivers actively flowing across its surface. Pluto is frozen solid, much smaller, and sits in the outer Kuiper belt, 3 billion miles further from the Sun. What they share is atmospheres dominated by nitrogen and methane, and surface chemistry that has been evolving for billions of years. This has happened in environments with no free oxygen. Whatever this mystery molecule is, it appears to be tied to that ancient methane and nitrogen chemistry. This is the kind of chemistry that may have paved the road toward life on the early Earth. The researchers say the Dragonfly mission could eventually help narrow this down by analyzing Titan surface materials directly. But that mission is still years away, and even when it arrives, it cannot observe the specific spectral signature in the way Webb already has. For now, the unidentified molecule sits on two very different worlds, matching nothing in our scientific catalogs, waiting patiently for an explanation. And Pluto oddities do not end with its atmosphere. If you have been following along thinking this is just one weird paper stacking on top of another, hold on. We are about to put the entire picture together. And if you have not yet hit that subscribe button, do it now. The next few minutes are the part of this story that completely changes how Pluto fits into the future of space exploration itself. Let us talk about the surface. The heart-shaped plane from New Horizons is officially named Tombaugh Regio, after Clyde Tombaugh. The pale western lobe of that heart, Sputnik Planitia, is a basin of nitrogen ice roughly the size of Texas. Its surface is visibly churning in slow convective cycles. Warmer material rises and cooler material sinks. These patterns of circulation look strangely similar to boiling water on Earth, except the heat driving all that motion appears to come from the slow radioactive decay of elements inside Pluto rocky core. This core sits hundreds of miles below the ice. That means one very important thing. The inside of Pluto has not finished cooling down. A world that everyone assumed was geologically dead is in fact still moving. It is still reshaping itself, still pushing heat up through its frozen skin. That internal warmth leads directly to one of the most debated ideas in planetary science today. Multiple independent lines of evidence suggest that somewhere around 100 miles beneath Pluto's frozen surface, there could be a liquid water ocean. The evidence is not a direct detection. It is a pattern. Cracks and ridges across Pluto's surface align in ways that match what you would expect from a subsurface liquid layer, slowly shifting and flexing. Sputnik Planitia sits directly above what appears to be a positive gravity anomaly. This is a place where the mass below the surface is denser than the surrounding terrain. On a tidally locked world like Pluto, heavy features naturally rotate over time to face the largest gravitational influence nearby. Sputnik Planitia faces directly toward Charon, and that is exactly where it would end up if something dense and liquid sat beneath it. This suggests a slow pulling of that section of the crust into position over hundreds of millions of years. Then there are the cryovolcanoes near Pluto's South Pole. Two enormous, isolated peaks rising between 13,000 and 20,000 feet. They have deep depressions at their summits and flanks that show patterns resembling cooled flows. If these are genuine cryovolcanoes, then at some point a thick slurry of water and ammonia was forced upward from a deep liquid reservoir. Something warm enough to be liquid existed inside this frozen world and may still exist there today. That matters enormously for how we think about liquid water in the outer solar system. Hidden oceans are already confirmed or strongly suspected beneath Jupiter moon Europa and Saturn moon Enceladus, both of which show dramatic surface evidence of all this activity. Enceladus erupts literal geysers of water vapor into space from cracks near its south pole. Europa shows surface patterns that closely resemble broken sea ice in the Arctic on Earth, strongly implying movement of liquid water beneath. But there's a huge difference. Europa and Enceladus are both close to giant planets whose tidal forces flex and squeeze their interiors. This generates the friction that keeps their inner oceans liquid. Pluto has no such large neighbor doing that work. It is too small, too far away from Neptune for tidal squeezing, and it sits out in the Kuiper belt mostly alone. If there really is an ocean under Pluto ice, it would be kept liquid by radioactive decay alone, which would mean that even on a small frozen world billions of miles from the sun, the heat produced by decay is enough to maintain liquid water. If that turns out to be true, the list of places in the solar system that could be hiding liquid water grows dramatically. Every large icy object in the Kuiper Belt suddenly becomes a candidate, and there are hundreds of thousands of those objects out there. And then there is one of the strangest landscapes ever photographed in the solar system, a region called Tartarus Dorsa. New Horizons captured tall rows of jagged blades made of frozen methane, arranged in long parallel ridges. Some reached more than 2,800 feet into the thin Pluto sky. Nothing like them had ever been photographed anywhere in the solar system before. Researchers believe they formed through a process similar to the penitent ice formations found in high-altitude deserts here on Earth. On Earth, those penitent formations grow no more than a few feet tall. On Pluto, the same basic process runs at an enormous scale, using methane ice instead of water ice. A 2025 reanalysis suggested these blade fields may wrap around as much as 60% of Pluto equatorial belt. This forms an almost complete ring of jagged frozen terrain circling nearly the entire dwarf planet. And there's more. Pluto, steady leakage of methane into space is roughly 1.3 kilograms per second. This is being captured in tiny amounts by its moon Charon weak gravity, where it freezes onto its cold poles. It is then transformed by solar radiation into permanent dark reddish organic compounds. That is the mechanism behind those stains New Horizons photographed a decade ago. Webb has now confirmed the geometry and the chemistry of that transfer in far more detail than anyone had before. Put all of this together, and the picture of Pluto looks almost nothing like the picture we carried into 2015. Not a cold, dead, distant chunk of ice sitting silently at the edge of the solar system. A world running a completely unprecedented atmospheric cooling mechanism, confirmed by Webb in 2025. A slow chemical machine producing organic compounds in the same broad family as prebiotic molecules relevant to the origin of life. A world quietly bleeding its own atmosphere onto a neighboring moon, permanently staining Charon poles reddish-brown. A world hiding a completely mysterious surface compound that also shows up on Titan and matches nothing in the scientific literature as of 2026. A world wrapped in jagged fields of towering methane ice blades visible from orbit. And a world with strong, growing geological evidence pointing toward a hidden liquid ocean deep beneath its frozen shell. None of this has changed its official label. Pluto is still a dwarf planet under the International Astronomical Union current definitions. That debate occasionally resurfaces when scientists or NASA leaders call for the definition to be revisited. But it is a separate conversation from what the science itself is actually showing us. The classification describes Pluto as small, cold, distant, and unimportant. The actual data describes Pluto as active, complex, chemically rich, geologically alive, and still generating brand new discoveries in 2026. Webb is expected to continue observing Pluto periodically as it comes back into optimal viewing position. Each new observation adds new data points. Thermal light curves track how Pluto heat emission changes as the world rotates. These are sensitive enough to reveal variations between different terrain types, letting researchers build a more detailed picture. The Mystery 5.11 micrometer absorption signal will be a target for follow-up investigations through additional Webb observations, and through laboratory chemistry experiments aimed at synthesizing candidate compounds to check for a matching spectral signature. There is currently no funded mission in development to send an orbiter or a lander to Pluto, largely because the travel time is too long. Even with carefully planned gravitational assist from Jupiter, it runs to a decade or more. Space agencies have to weigh that against faster opportunities closer to home. The most recent Planetary Science Decadal survey identified a Uranus orbiter and probe as the top recommended flagship mission. Ice giants are considered a higher near-term priority than the Kuiper Belt. That priority may change as the complexity of Pluto and similar Kuiper Belt objects becomes clearer and clearer. But it is the current reality, and it means Webb is the only instrument reading Pluto in real detail for the foreseeable future. Every observation it returns from that direction now matters more than it would if a dedicated mission were already on its way. So here's the picture we are left with at the end of all of this: a world that was formally dismissed, demoted, voted out of the Planet Club in 2006, and then largely forgotten. A world that spent 85 years after its discovery sitting unexplored, expected to be geologically dead and atmospherically trivial. A world that was supposed to be hiding essentially nothing has been hiding almost everything. And now, instrument by instrument, observation by observation, the James Webb Space Telescope is revealing its secrets. This small, frozen world on the very edge of the solar system has been quietly doing things that no other world in the solar system does. This includes some things that science itself does not yet have the vocabulary to fully describe. Pluto was supposed to be the end of the solar system, a footnote, a frozen curiosity. Instead, it is becoming something far more interesting than that. It is becoming one of the most revealing places we have ever studied, A living chemistry lab, a hidden ocean candidate, and a window into what Earth's atmosphere may have looked like before life ever began. It is a quiet mirror held up against everything we thought we knew about how small, cold, distant worlds are supposed to behave. It turns out we were not looking closely enough. We just were not. And the moment we finally did look closely, the universe answered back with something that should genuinely change the way we think. This change should reflect what is possible on worlds we used to ignore. Pluto is not the end of the story. It might be one of its most surprising beginnings.